Hey folks, I'm continuing the homework question video here. This is in the second Jamboard for the Unit 3 homework questions, and we are wrapping up a little bit from Lesson 9 and all of the questions from Lesson 7, or 6 and 7, pardon me. So this one is page 496, number 9, and there was a number of different pairs of lines, and you were to figure out if they are skew. Now remember that if they're not scalar multiples in your direction vectors, so here for the first one, looking at the two direction vectors up there, if those direction vectors are not scalar multiples, then they're either intersecting or skew. So you have kind of the two choices, that the lines could cross somewhere in R3, or that they, and this is kind of hard to draw, that they would not cross and would be going at different angles and keep distance from each other. So remember that the way that we do that is basically setting the parametric equations of each one, and I've put the solutions that are in Miss Borth's solutions here just because I didn't think I'd get to write them all out in this amount of space. It's a little bit easier to see here. So here for the first one, we've got the parametric equations for x and for y and for z. Now each of the parametric equations for x and y, when we set them equal and solve, we get p equals q and p equals q. So everything else cancels out because those are similar, kind of similar components there. But that tells us something also, right? We know that p and q are the same, so then we can substitute in a p where that q is in the z equation where those are equal, and then solving we get p equals 1. So then we know q is also 1, and if we can find values for those parameters, so those variables in our parametric equations, the s or t or p or q, if we can solve for those, then there is a point of intersection, and we just sub those back in to find the value, and that tells us for sure that those lines are not skew because we found a POI. The next one for B, again, we're kind of setting up our x equation and our y, our z, pardon me, but the y is a little bit different. Both of the direction vectors in the two lines have a 0 for the y component. So both of those parametric equations for y would just be y equals 1. So we don't actually have to do anything with the y. We can just solve for the t and the s using the two equal equations from the x and the z components. Then we solve and we get t equals 4 and s equals 6, and you can sub those in to get the x and z values. We know that y will just always be 1. Here's something that Miss Borth did in this one for the solutions, which is kind of nice. She's plugged in t equals 4 into the first parametric equation, and also s equals 6 into the second, and just confirming. That's a nice check there that she got 8 for the x value in both parametric equations, and she got 22 for the z value in both. So that's kind of another double check that you haven't made an algebra mistake when you were solving. For part C, we have, again, setting the x equations and the y equations equal to each other, solving this system of two equations and two variables. We get p equals 1 and m equals -1, and then you have to check, does that work in the z's? So I'm plugging in -1 for m and +1 for p, and the z is both 0 in that case. So I think this has been cut off, but you would also, these are not skew. If you wanted to find the POI, you'd have to sub in the p equals 1 or the m equals -1 back into the original components for x and y, because we only have the z component solved there. The last one is actually skew. So we do the same idea here. Our x components, or our parametric equations for the x components equal, the parametric equations for the y components are equal, and in the y, because of that 0, this is a little bit simpler, like one of our y's is just equal to 1, so that's an easy one to solve for s. Subbing that value for s back into the equation from the x components, we get m equals -1, s equals -1. And if you check that now in the z's, you get two different numbers. So these are skew lines. You have to be able to solve for the two parameters, sub it into the equations of the component you didn't use. Normally I use x and y and then sub it into z. So those would be skew lines. Okay, next one, show that these lines lie on the plane. So I want to write these lines with, I want to write them in vector form, I think. So here, I would say for L1, x over 1 equals t, y minus 7 over -8 equals t, and z minus 1 over 2 equals t. And then rewriting that into kind of a nicer form, 0 plus 1t, y equals 7 minus 8t, and z equals 1 plus 2t. So the vector equation of this line 1 is 0, 7, 1 plus t times 1, -8, 2, where t is any real number. Then I'm going to do the same thing for my second line for L2, but I'm going to use a different parameter. I'll use an s. Remember, you don't want to mix up like having the same variable in each one. So here I would have x minus 4 over 3 equals s, z minus 1 over -2 is s, and y equals -1. I'm going to say plus 0s. So here x is 4 plus 3s, y is 1 minus 2s, and then the vector equation here of this is going to be 4, 1, -1 plus s times the direction vector there. So what I really want to show is that these lines here lie on that plane. And I am going to need, I think, actually quite a bit more space here. So I'm just going to add in a slide and copy some of my work up there. So kind of two ideas just to sort of talk about what we're going to need to show that those would be on that plane. The first thing, we know that all of the vectors that lie on the plane would be perpendicular to the normal. So we would know that those vectors would all be perpendicular to the normal vector. So that's the first thing we could do to show that those vectors were on that plane. Double checking that they're the direction vectors are perpendicular to the normal. And I'm just kind of swapping some of this out. But it's possible for the lines to be parallel to the plane and not actually like lying on the plane at all. So the two things we're going to look at is the direction vectors. So is the direction vector perpendicular to the normal of the plane? And the second thing we're going to do is the point, which we know is our position vector, on the plane. And if both of those things are yes, then that will be on, that line will be on the plane. So I've copied these up here. So the first thing I want to check for L1, for L1 I want to check is the position vector, and I know my normal here would be 2, 1, 3. So is the position vector perpendicular to the normal? So I'm going to do 1, negative 8, 2, dot 2, 1, 3. So that would be 1 times 2 plus negative 8 times 1 plus 2 times 3. So that's 2 minus 8 plus 6, which is 0. So my direction vector is perpendicular to the normal. So I know that this line is at least parallel to the plane. I don't know for sure yet that it's actually on that plane, but it might be. The next thing I'm going to check is kind of like a left side, right side check of this equation of the plane. And I'm going to check the point that I have and see, does that work as x, y, z values in the equation of the plane. So the left side is 2x plus y, 2x plus y plus 3z minus 10. So here I get 2 times 0 plus 7 plus 3 times 1 minus 10. And yes, that equals 0. So the point is on the plane. And my direction vector is perpendicular to the normal, because the dot product was 0. And it really requires some like conceptual understanding here of what these pieces of the line are. So if you want to show that this line is on the plane, we have to know that the point on the line is on the plane, because that tells you kind of the difference between, like, is the plane here and do you have a line like up here? Because that could just be the direction vector perpendicular to the normal but up above. We want to show that the line is exactly on the plane, because we're checking that point. Is that point that we know on the plane, and also is the direction vector perpendicular to the normal? So does that make that 90-degree angle? So those are really the two things we're going to look at. We can do the second one as well from the other equation for line 2. Now we want to double check, is the direction vector perpendicular? So 3, negative 2, 0 dotted with the normal. So 3 times 2, and I'm not getting it. Does this say prove that it is? Show that these lines lie on the plane. Okay, so I am not getting this, but I wonder if I've made a mistake in my work. So just 1 second. Oops, sorry guys, I did find my error here. I had written these in, when I was looking at the parametric equations, I'd written the x and the z because y was just equal to negative 1. So I had these out of order, and then I put them out of order in there. Whew. Okay, so sorry. This one, I just kind of was like alphabetical order, but then it wasn't. So that's z equals 1 minus 2s. Oh my goodness. So these guys are just switched around. So it was because the y was written last, I was going a bit too fast and did not pay close enough attention there. That's 1 and -2. So now this line is 4, -1, 1. These guys are switched, -1, +1, and then 3, 0, and -2. So I had the wrong order here. Goodness. 0, -2, and then if I swap this order around, then I think we work out. So then I've got 0 times 1 and -2. There we go. Whew. It is perpendicular. So then I get +0 plus -6, which is 0. So that is perpendicular to the normal. And then we can also double check that the point is on the plane. And I will kind of left side, right side this again. So that's just 0. Left side is big. We've got 2 times 4. Using just that one point. Plus y is -1 plus 3 times 1 minus 10. So here 8 minus 1 plus 3 minus 10 is 0. So therefore both lines are on the plane. Now, I think that there was another part. This is a monster question here. It also said that we were supposed to determine the point of intersection of the two lines. So I will copy that again, and we can go through that on the next slide. Just let me correct the mistake I made on that last one. So if we wanted to find POI, here we go. I have these two lines. I know that I need to write them both. A little bit messy, sorry. I need to write those both in parametric form and then solve for POI. So this is part B. So here I get x equals t, y equals 7 minus 8t, and z equals 1 plus 2t, where t is a real number. And over here, I get x equals 4 plus 3s, y equals -1, and z equals 1 minus 2s. So I'm going to make my three equations from setting those pairs equal. So here I have that t equals 4 plus 3s. The next pair, looking at the y's, and this is actually going to be an easier one. So 7 minus 8t equals -1. Once I get those two pairs, I'm going to just solve this because I only have a t there. So -8t equals -8, so t equals 1. And then I'll sub that back in and solve for s up in the first equation. So here 1 equals 4 plus 3s. So -3 equals 3s, and s equals -1. So if I have s equals -1 and t equals 1, I just have to check my z's and make sure that they both give me the same value. So if z equals 1 plus 2t, then it's 1 plus 2 times 1, which is 3. And Z also equals 1 minus 2s, which is 1 minus 2 times negative 1, which is 3. So I know my point of intersection. I know the y. And if x equals t, then that's just equal to 1. So the POI, I'm getting this from a bunch of places. I knew y was negative 1 at the start. X was t, which is just 1. And I've solved for z, which is 3. So my POI is 1, negative 1, 3. Next one. And this is looking at the next section of homework on the intersection of planes. So considering the following systems, 2x plus y plus 6z equals p, and x plus my plus 3z equals q. So let's determine values of m, p, and q such that the two planes are coincident. Okay, so that would mean that they have to be exactly the same equation. So if we look at the components or the terms where we know both, we can kind of clearly see that the x coefficients are doubled in plane 1, and so are the z coefficients. So we could say that for part A, I could say that 2m would have to equal 1. So m would be 1/2 for sure, that is the only value. And then I would also say that doubling this one, that I would have 2q equal to p. So whatever q is, I would double it to get the p. But it actually doesn't matter. These are not going to be unique. As long m is unique, that has to be that value. But this could work for any p and q values where this holds true. The q just has to be half the size of p. P is the doubled q value. Okay. Determine values of, for part B, m, p, and q such that the two planes are parallel and not coincident. So that would be kind of the same idea. Like the normals would have to be scalar multiples. So we would still have this m being 1/2 because we've got that relationship, but p and q would just not be following that rule. So we'd have m is 1/2 and p is not equal to double the q value. So it's not unique. Any one where m is 1/2, that has to be set, but the p value is not double the q value, would be parallel and not coincident. Okay. And for C, a value of m such that the two planes intersect at a right angle. So here we would have n1 dot n2 would have to equal 0. And we know n1 is 2, 1, 6, and n2 is 1, m, 3. So we'll just do that dot product and see where that would equal 0. So 2 times 1 plus 1 times m plus 6 times 3 equals 0. So that's m plus 20 equals 0. So m would have to equal negative 20. And determine the values of, so that would have them intersecting at right angles. So for D, it says determine values of m and p and q. And p and q don't come into play here. They would determine where these planes would intersect, but the right angles is only determined by the dot product of their normals equaling 0. So for D, m equals 20, negative 20, and p and q could just be anything. It's not unique. They actually don't matter much at all. Number 11, the line of intersection of the planes given here is L. And we want to determine parametric equations for L. So we know that if we are trying to figure out the equations of the intersection of planes, we can't find one specific equation. There are an infinite number of possible equations where that would represent this line. So remember that there's no unique equation for a line in R3. So I'm going to set this up and say that this is a point plus t times this. And we can pick any point on this line, and we can pick any scalar multiple of the direction vector. So any point and any scalar multiple of that. We are going to fairly arbitrarily choose the point where z equals 0 and the scalar multiple of the direction vector where z equals 1. So we're going to have an x equals, y equals, z equals, and the z is 0 plus 1t, which is really just z equals t. We have an infinite number of possibilities. We just have to pick one. Again, you don't have to pick this, but it makes it so much cleaner and nicer. I could pick the point where z equals negative 12 and the scalar multiple where this is 0.625, but that's just going to make my math messier. So I'm going to pick a nice 0 there and a 1 in there. Now going back to, with this z equals t, going back into my original planes, I will write those equations substituting in the z equals t. So 2x plus y minus 3t equals 3. And then x minus 2y plus t equals negative 1. So I need to be able to do substitution or elimination to clear out one of these variables. So I'm going to multiply the first equation by 2. So I'll get 4x plus 2y minus 6t equals 6. And then we can eliminate those y's if we just add down in that column. So here I get 5x minus 5t equals 5. So I'm going to solve this for x. So x equals 5x equals 5 plus 5t, or x equals 1 plus t. So now I have an x in there, and I can put in the x component of the point is 1, and the x component of the direction vector is also 1. Now I just have to substitute this x value into either one of the two equations up at the top and solve for y. So I'm going to use that first equation, 2x plus y minus 3t equals 3. And if x is 1 plus t, I get 2 plus 2t plus y minus 3t equals 3. So y equals, so that would be 3t minus 2t on the other side, t plus 1, or 1 plus t. So y is the same there as well. And typically these will be kind of chosen that give you some pretty nice numbers there. So here, the next part I'm going to, I think, have to do on the next slide. Some of these are very big questions. But we'll do this on the next slide. So we want to find if L meets the xy plane at point A and the z-axis at point B, determine the length of line segment AB. Okay. we'll go take this 1, 1, 0 and 1, 1, 1. That's a pretty easy. Here's my line. 1, 1, 0 plus t times 1, 1, 1. So we want to know if this meets the xy plane at A. So we want to find point A. So the xy plane, we know our values here. X was 1 plus t, y was 1 plus t, and z was just t. Now, if something is on the xy plane, then we would know that the z component of that point was 0. So we know z equals 0, which tells us t equals 0. Then we're going to find the x and y components of that point. So if t equals 0, x equals 1, and y equals 1. And then the other piece of that is we want to know where it would meet the z-axis. So if it meets the z-axis at point B, we know that the x and the y components are 0. So 0 equals 1 plus t, and 0 equals 1 plus t for the x and y. Because those are the same, t would equal -1, and we know that z equals t, so z is -1. So that would be point B. So I have point A and point B, and then it's just asking me for the length of line segment AB, which is really kind of the same as vector AB, the magnitude of vector AB. So I can find this vector. It would be -1, -1, -1, and then the magnitude of the vector is the square root of each of those squared. So the magnitude of that line segment, or of the vector between point A and B, is √3. And last question. This one says, determine the Cartesian equation of the plane that is parallel to the line with this equation and contains the line of intersection of these two planes. Okay, so if we have something parallel to this line, we want to get this line into a form that we can more easily identify the direction vector. So it doesn't even look like symmetric equations as much because we don't have fractions, but it's actually just much more simplified. So this line, we could say that x equals t, -2y equals t, and 3z equals t. So I could rewrite that as x equals 0 plus 1t, y equals 0 minus 1/2 t, and z equals 0 plus 1/3 t. So we could write this line as 0, 0, 0, it goes through the origin, plus t times 1, -1/2, and 1/3. Now I don't love those, the fractions there. And because that's the direction vector, I know I can just do any scalar multiple. So I'm going to rewrite that, whoops, forgot my t, and just multiply all those guys by 6. So it would be 6, -3, 2 as my direction vector. So this is one of the direction vectors on the plane. Okay. We also need to know the line of intersection of these two planes. So if we're looking for an equation of a plane, we need a point and two direction vectors. The direction vector of this line is one of those. Okay, the next thing we know that it contains the line of intersection of these two planes, and we know a line has a point and a direction. So we've got this direction vector and then the point and direction vector from the other one. So again, whenever I'm doing the line of intersection, I'm going to just kind of form, I have t's used already in there, I'm going to form something like this where I just pick a 0 and a 1 there. So I know I have x equals, y equals, and z equals 0 plus 1s, or just s. Okay. So from these equations, I'm going to figure out what x and y are. X minus y plus s equals 1, and 2y minus s equals 1. So I can just solve this. Y equals 1/2 s. So y is going to be 0 plus 1/2 s. And then if I plug that all in and solve for x in the other one, I'd have x minus 1/2 s plus s kind of coming down from there equals 1. So x equals 1 minus 1/2 s. So this point would be 1, 0, 0, and the components here would be -1/2 and 1/2. So again, I don't love this with the fractions. I feel like that's messy, especially if we need Cartesian equation. That's going to be bad news. So I'm going to rewrite this, just multiplying that direction vector by 2 to clear out the fractions. You can never multiply the position vectors, ever, ever. These can't be scalar multiples. That's an actual point. But direction vectors, no problem. So -1, 1, 2. That's a little bit nicer. So now I want to find basically the Cartesian equation and I have this point 1, 0, 0 and two vectors, two direction vectors, the -1, 1, 2, and from the other one 6, -3, 2. So I can go on to the next slide, and we'll find the normal, which is A cross B, and we'll do the cross product here. 2 minus -6 is 2 plus 6 is 8. Then 12 minus -2, which is plus 2, so 14. And +3 minus 6 is -3. So my normal is 8, 14, -3. And then we just have to plug in the point to find my d. So 8, x plus 14y minus 3z plus d equals 0. And my point was 1, 0, 0. So 8 times 1 plus 14 times 0 minus 3 times 0 plus d equals 0. I get d is -8. So the Cartesian equation is 8x plus 14y minus 3z minus 8 equals 0. And it's in the proper form. Remember to double check for positive leading coefficient, clear out any fractions, and reduce it if it's not in lowest terms.